Okay, hello everybody. Welcome to the robotics session in this SmartFest. I am Francisco Melendez. My role in Fiverr is the technical expert and evangelist that takes care of the robotics roadmap. The session today we have prepared will elaborate a bit more on the topics we have presented in the opening session before this afternoon. And we will be elaborating on the vision that Fiverr is building around the concept of agile production and the contributions that our ecosystem is making to the open source robotics technology. In particular, we have three speakers. The first one is José Antonio Amaral from Proxima. He's a software engineer, quite experienced in C and C++ development, and he's working in a particular integration service that is quite relevant and instrumental to the future of the synergies, let's say, between ROS2, DDS, middlewares, and the Fiverr ecosystem. He will be elaborating on all the technology they are developing in the Proxima, one of our members in the Fiverr Foundation. And then we will move to two particular use cases we are developing in production environments. The first one is RoboWelder, which deals with problems associated with flexible robotics-based welding. And for this, we account with Orpheus, and Orpheus is a PhD senior roboticist that is the main developer in this project. He will explain which is the special particular microservice he is developing in this project, but also some of the specific problems they are dealing with in a real manufacturing company called Carel. Then the final presentation will be carried out by Magno, and Magno comes from Portugal. He is a senior researcher and the manager of the development team in Introsys. He has a robotics background, but then he got particularly specialized in computer and machine vision systems, and precisely the FireFit project has very much to say regarding the quality control of packages in automated production lines. So this is the content of the session today, and what we can do is to start as soon as possible in order to have some time for the final questions and answers with José Antonio. So please, José Antonio, once you're ready, take the stage.
Thank you, Francisco, for the introduction. I'm going to share my screen now, and we can start. Can you see the presentation already? Great. So hello, well, as Francisco was saying, I am Jose from the Proxima, and in this presentation I'm going to talk about open middleware technologies for smart robotics. We are covering mainly two aspects here in the presentation. One of them is talking about MicroROS, the MicroROS middleware, and why is it important in the frame of robotics. And then how to integrate MicroROS with the Fiverr Context Broker and all the technologies involving the Fiverr ecosystem. Then, following the presentation and talking about the first aspect of it, I would like to introduce, for those who doesn't know it yet, what is ROS2. ROS2 is a middleware focused on developing solutions for robotic applications. It is based on DDS, the Data Distribution Service, which is a very well adopted middleware standard on which Proxima develops FastDDS, which is an open source solution for distributed systems. And ROS2 is built on top of that to give users an easy framework to develop their robotic applications and solutions. What is the problem with ROS2? Well, the main problem is that it is a very big middleware, and it is not suitable for real-time applications or for being, so to say, embedded in a very small device, such as a microcontroller. This is where MicroROS appears as a joint effort between the Proxima, the Fiverr Foundation, the Opera European Consortium, and other enterprises as Bosch or PIAP as an open source project which fits the gap between ROS2 and microcontrollers. MicroROS allows users to take advantage of the full potential of microcontrollers and ROS2 in the embedded world. It is thought to be to take care of all the resources needed in the embedded world, such as, so to say, using static memory, about using dynamic memory, and it is thought to be very portable to a lot of embedded platforms and to being able to run on top of several protocols such as TCP, UDP, etc. Well, MicroROS now is supporting ROS2 FOXI, and there are also the possibility to run it on top of ROS Galactic using also FastDDS as the RMW implementation of it. And we are also providing a rolling release, which is constantly updating, following the philosophy of ROS2 rolling. As I was mentioning before, some of the main features in MicroROS is that it is completely compatible with ROS2 layer by layer. It is very well integrated into ROS2 ecosystems and allows users to basically take advantage of all the functionalities that they would use if they were developing a normal ROS2 application on their laptop or computer. Instead of following a purely distributed architecture, MicroROS relies on top of a client-server logic, where there's an agent running on ROS2, which is listening for petitions coming from a MicroROS client, which is written on C99. And the agent is acting as a proxy for the microcontroller to act on behalf of it in the ROS2 data space. As I was mentioning also before, the transport is fully customizable. MicroROS allows you to fine-tune how much memory are you using of your microcontroller based on the ROS2 entities you are creating. It can be run on top of bare metal, including Arduino, or on top of a real-time operating system such as FreeRTOS, Zephyr, and NATEX. And it is very well thought in terms of the build mechanism to be able to use cross compilers to easily build it and deploy it on your microcontroller. Proxima mainly provides the middleware, which is running underneath MicroROS, which is called the MicroExaCDDS, and it is nothing but DDS for extremely resource-constrained environments. And this middleware is based on a client-server architecture where there are clients, so to say, running on top of IoT devices or microcontrollers on a very lightweight CV99 library. And these clients are interacting with an agent, which is then translating all the information coming from clients, from sensors, actuators, or whatever, to the DDS data space so that it can be consumed by other DDS entities. As DDS is the middleware underneath ROS2, this makes MicroExaCDDS very suitable to be the default middleware for MicroROS, and so to be able to speak with the ROS2 data space. A big advantage of MicroExaCDDS is that it is connection-oriented and allows you to keep the status of the microcontroller application even if the microcontroller enters in a deep sleep state, thanks to the agent keeping track of it. This is especially advantageous because if the microcontroller wakes up again, it will fetch its last status from the agent, and it will be able to run from that point on. Now that we know a little bit more about MicroROS, I would like to speak about how to integrate it within the FireWire ecosystem. And to do it, Proxima is also providing an open source solution, which is called the Integration Service. And this is nothing more than a tool that allows you to integrate a number of arbitrary protocols to speak between them. These protocols are meant to be, for example, protocols are incompatible in principle, such as, for example, ROS1, ROS2, the firewall context broker, even WebSocket connections. Or you can have applications running on the same protocol, but, for example, located in different wide area networks, or even located in different logic regions, such as, for example, 2 different domain IDs in the case of DDS. To know a little bit more about how integration service works, I would like to tell that it is divided in a core library, which speaks a common representation language, which is X-Types, also a library developed by Proxima, and which is completely open source and based on the X-Types DDS standard. And this common language is then used to trespass the information between one protocol, one middleware, and another. What is happening here is that, for example, if you have a user application based on the publisher-subscriber paradigm and want to communicate it with another application running on a different middleware, integration service is creating for you a mirror entity on the red box to listen to your publisher application in the blue box, and then vice versa. If you have a subscriber application in the blue box, integration service is creating for you a publisher to send data to this application. The libraries responsible of creating these mirror entities to communicate between a specific middleware and the core are called system handlers, and our box will provide support for fast DDS, fireware, ROS1, ROS2, and WebSocket. But more will come regarding the necessities of users or even the contributions from the community. I would like to show you, an example of how this could be used to communicate 2 ROS2 applications that are running on different local area networks. Here, the integration service is translating ROS2 messages into DDS messages, and then using fast DDS capabilities for a wide area communication, we are sending the message to another PC located in a different local area network. And then the message is being translated back to ROS2 to the listener. So the result here is that there is a first operator using a joystick, as you can see in the animation here. And he's moving a Turtlebot autonomous base, which is on the house of the second operator. You can see here that he's putting his hands on his face, so no cheating. He's not moving the autonomous base. It is actually being moved by the first operator. And finally, I would like to speak a little bit on how this could fit within the firewall ecosystem. So we have a firewall system handle, which is capable of sending updates to the firewall context broker and also listening for incoming updates from the firewall context broker. So what can be done here, and we have actually a very nice demo which depicts this, is to get these updates and send them to the firewall system handle run by the integration service, which will then translate these firewall specific messages to ROS2 messages so that they can be consumed by applications running on top of ROS2, and vice versa. We can send the information from ROS2, and then thanks to the integration service, this information will be posted on a firewall context broker so that users can take advantage of this information. And of course, being able to send information from ROS2 means that you can send information from MicroROS, because the communication between MicroROS and ROS2 is transparent regarding user side. So that will be everything from my side. I think questions will come at the end of the presentations.
Yeah, José Antonio, thank you very much. Yes, we will do the questions and answer session join all together after the 3 presentations. So I guess it is now the turn for Orpheus to present RoboWelder. Whenever you're ready, please go ahead.
Yeah, thank you, Francisco. I'll just share my screen. Can you see my screen okay?
Yes, we can see it.
Okay, great. Thank you for attending my presentation. My name is Ofes Kypris, and I am a research engineer at I Know How SA. And I'm also the technical lead of the RoboWelder project. Today, I'm going to be talking to you about how to make shipbuilding for custom parts more agile and streamlined using a combination of robotics, AI, and cloud deployment. So let's talk a little bit about the business scenario and the motivation for this work. Over the past decades, and with advances in mass manufacturing, industry has proven it can benefit greatly through the introduction of robotics in the workflow. In robotic welding, particularly in the automotive industry, robotic welding leads to measurable improvements, which is elimination of hazards in the workplace, improved process feedback and analytics, increased product quality, and increased revenue. However, in the shipbuilding industry, things are a bit different. Automation has not made its way into the space, and welding is largely still a manual process. And welding for small production lines with custom parts is a challenge. Robotic solutions exist, but they are dependent on CAD models, which often don't exist. And if they do exist, bad alignment between physical target and CAD model is a problem. Then you have legacy and unintuitive HMI systems and no open standards, which make the robotic systems limited in their use. So we teamed up with our end user, Carel SA, which is a shipbuilding SME, to build an autonomous system for welding of custom parts. The agreed upon requirements are the following. First, the ability to create a 3D model of a part from scratch to enable custom jobs. Second, automatic proposal of weld seams. And third, the path following of the proposed weld trajectory so that the robot can weld the part. So our process can be split into three main parts. And these are our flexible automation capabilities. And they are the following. The first one is robotic photo capture and 3D reconstruction, where the target object is photographed and rendered into a 3D model. The second one is the weld seam proposal, where our deep learning architecture detects candidate weld seams. And the third one is the path planning and path following, where the robot calculates the optimal path for welding the detected seams. So the end goal, of course, is to weld the part. And here you can see all stages of the process, from upper left, where it's the model generation and weld seam proposal, to the middle, where we are path following the generated path and welding the part. And finally, on the right, you can see the welded workpiece. So to build our system, we use a sophisticated combination of hardware and software. The system comprises of a Universal Robots 10E robot, a DSLR camera, as well as a custom designed peripherals for holding the torch and camera. Our software is architected into microservices and is firmware enabled and GSI compliant. It comprises of a robotic control module architected on ROS, a 3D reconstruction module with an Alice Vision Mushroom backend, which performs the photogrammetry, a weld seam proposal module that uses a modified version of Facebook's VoteNet algorithm. And also we can seamlessly send data to Grafana for visualization of process information. That we achieved via our custom NGSI clients and also via FiROS. So let's talk a little bit about context data that's consumed and context data that's generated in our platform. So the consumed data can be seen on the left, the generated data can be seen on the right. So for the first part of the process, we basically give it a target volume and center, and it produces a time series of robot joint poses, the 3D reconstruction status, and the 3D reconstructed model. The second part, which is the weld seam proposal, takes in the 3D reconstructed model and outputs the candidate weld seams. And the third, which is the path following for welding, takes in a simplified 3D reconstructed model, which is used for path planning, and the candidate weld seams. And it outputs a time series of robot joint poses during the path following for welding. So in the future, we plan to encapsulate additional context data in the future. The first chapter will be a welding decision support system, where the optimal parameters for welding can be stored and reused. The second chapter will be a tool for volumetric weld inspection, which will be able to compare a 3D model of the part prior and after welding in order to produce useful statistics pertaining to weld quality, such as weld volume, contour, and alignment. Let's talk a little bit about the architecture, the overall architecture of our system. On the upper left, you can see within the ROSE AP grid, you can see the cloud deployment. This is a containerized app, which is deployed on the cloud, and it contains a coordinator module, which coordinates the 3D reconstruction and weld seam proposal processes. And it's important to mention that the software and as well as our hardware peripherals broadcast data to the Orion Context Broker in NGSI version 2 format. That makes it easy to visualize process information on Grafana. On the lower right corner, you can see a 3D tracking module that uses the HTC Vive tracker hardware. And this has been a driver has been developed for this, but we have not integrated that yet into our system. This is part of future work, which I will talk about later. So, as I said before, we have bundled some of the functionality of our system, namely the 3D construction and weld seam detection, into a containerized package, which we call the ROSE AP. The inputs to the package are photos of the object and the associated camera poses in the world coordinate frame. That's the coordinate frame of the robot. And the output is a 3D reconstructed object with proposed welding trajectories. So our code has been made publicly available on GitHub, and it's under an Apache license. In the repository, we provide, among others, the containerized app. So it's fully Dockerized. And we provide example data for injection, which can be seen on the right. And data injection scripts, so that the data can be used and injected into the component. And we also provide extensive documentation and user manuals. It's important to mention also that in our repository, we provide three test examples, which are characteristic of what our software can do. Two of them are so-called good, so they use appropriate data inputs, and one of them is bad, produces a less appropriate 3D model in order to demonstrate what should not be used as an input. So in the future, will we refine the 3D reconstruction subsystem to increase the 3D model accuracy, which means we might replace it with a structured light or LiDAR modality. Also, we will integrate our laser profilometer in order to increase our surveying accuracy while welding. And most importantly, we will integrate the HTC Vive tracker in order to enable input of custom welding trajectories by the user. So as you can see on the lower left, the lower right corner, we have already integrated wrote the driver for it. It can broadcast data to Grafana, so XYZ position data. And on the left, on the upper right corner, you can see how the movement generates changes in positions in GSI v2 format. To close, I'd like to attribute credit to the technical team that made this project possible, namely Michalis Logothetis, our robotics engineer, Thanos Sakeliou, our AI software engineer, and Nikos Vamadonis, who is our lead mechanical designer. And with that, I would like to conclude my presentation. Thank you for your attention, and welcome any comments from the audience.
Great. Thanks a lot, Orpheus. Quite interesting, everything. And in fact, we can talk about this offline, but probably even MicroROS has something to do with your future projects, and we can build synergies between these two projects. But let's go with the third one, FireFit, which is presented by Magno. Please, Magno, whenever you're ready.
Yep.
Just
thank you, Francisco.
Take the floor.
I'll just, yeah, thank you. I'll just share my screen. Okay, I believe all of you can see it now.
Yes, we can see you.
Okay, thank you. So, hi everyone, good afternoon. My name is Magno Guedes. I'm a researcher from Introsys, and I'm here to talk about our experience with FireWare in a real case scenario, namely the FireFit project. So just to introduce a little bit the company, Introsys is an SME based in Portugal. Our main offices are located in Palmela, near Lisbon, and we have an R&D lab located in Castelo Branco, near the border with Spain. The company was founded in 2002 as a spin-off from Nova University of Lisbon. Our purpose at that time was to create affordable robots for humanitarian demining. Since 2004, the company changed the focus to become system integrators for the automotive industry, especially in the automotive sector, working primarily for Volkswagen, Audi, Ford, and BMW. Currently, we offer turnkey solutions, including the robot and PLC programming, electrical design and planning, virtual commissioning, mechanical design, project management, and training. To support the core business of the company, we have a dedicated department for research and innovation. Since the beginning of the company, we work on mobile robots. This is some of the examples that you can see. Our first robot at the center was designed for humanitarian demining. Later on, in the left side, you can see that we upgraded the robot to a more robust design, so it could be used for defense and surveillance tasks in rough environments. Later, we went to some more extreme conditions, developing a robot to collect soil samples in extreme environments. More recently, we've been using this technology. And know how to develop and integrate AGVs in the automation industry. It is also worth mentioning that the software and control used in all of these robots is powered by Roche. Other line of research emerged to answer real problems faced by our teams in the factories. Basically, to optimize their processes, we started to develop software applications to automate some of their tasks, aid their planning, and reduce the human error. Our portfolio includes software that parse and validate robot programs against the requests of our clients. We have software that is used to manage warehouse inventory across all projects and across all clients. And then we have also some software that is used to perform resource planning and project management, adjust to our business models and our work procedures. Also, under the Eisent brand, we work on new paradigms for Industry 4.0 and also industrial quality control. Here, we span across plug and produce distributed control, digitalization, and also quality assurance. We are concerned for this quality assurance. We are concerned with giving industrial robots proper perception and mechanisms to perform flexible and complex tasks, integrating computer vision and sensor fusion to perform robot guidance and non-destructive testing. Here in these pictures and in these animations, you can see some examples of projects that we worked on. From left to right, we used hyperspectral imaging to perform color inspection. We are using vision systems to validate robotic glue applications, also vision guided wheel picking, and quality inspection of welded parts. Sorry for the image, it's a little bit small, but this is a closed machine that uses a sensor to detect defects in welded parts. So now talking about the FireFit experiment. In the last few years, we understood that relying mainly in the automotive sector is risky. On one hand, people, especially in big cities, are buying less cars. On the other hand, the Asian market is growing rapidly and becoming more competitive than ever. So we extended our capability and our application domain to other industries with great potential for automation and robotization. With the help of the IH2, the European Union and FIWARE, we were able to prove this potential in the food industry through the FireFit experiment, which I will present in the next slides. So the motivation for this project relied on improving quality control processes in the food industry using FiWARE technology. Most of the processes, especially in traditional and small business, are manual and affected by human factors. We could observe that most labor is highly repetitive, leading to fatigue and lack of concentration, which results in unidentified issues, waste increase, and of course, loss of reputation. However, for most of these companies, investigating high-end automation technology may seem too unbearable, not at all affordable for small companies. So for this project, we worked together with our colleagues and end users from A. Pires Lourenço, one of the major ham producers in Portugal, to respond to the IH2 initiative and test a new FiWARE-based robotic solution for quality control of packaging systems in this sector. It was required that the solution could be affordable, easy to deploy and integrate with existing production lines, and be able to be tested without any change in the production process. Thus, we conceptualized 3 independent systems that we deployed at different stages of the production and provided both automated quality control and the robot-based sorting. So after slicing, we integrated a setup to visualize ham slices. After packaging and sealing, we deployed a setup to analyze the packages, and at the end of the line, before the boxing and shipping of the packages, we added a robotic sorting machine to automatically sort between good packages and defective ones. Regarding the quality inspection of ham slices, we relied on hyperspectral imaging using the obtained spectral signature to estimate the salt content. This salt content is believed to be the most significant factor to determine if the ham has been properly cured in this process. So for the packages, most of the problems are due to improper sealing, which may occur if the plastic is, for instance, folded, or parts of the hem reaches the sides, the borders of the package. As you can see in the image, the materials used are flexible and structured. So we apply the trained neural network to identify deviations on the visual features of what will be a properly sealed package. Both of these systems are triggered by sensors that are linked to the FiWare ecosystems through IoT agents. And also the inspection results are sent to the FiWare and handled by another logic unit, which we called the process controller.
Magno, we are running out of time. You have 1 minute.
Okay, I will just run a little bit. Okay, this is for the sorting. The sorting system comprises a SCARA robot and then a conveyor belt, and has a sensor that is placed at the end of the line. This sensor triggers the system to collect the results from the process controller and give that results according to the packages that reach the robot. The results will be okay or not okay. So the robot will know if he have to collect or discard that package. All of this communication is running in the FiWare ecosystem. Now going to the architecture. For each device we created an interface which translates device data to MQTT messages. Then still at the shop floor level, the IT agent connects to the MQTT broker and handles subscriptions and registrations of entities under our in-context broker, which lives in the cloud. So this communication solves our connectivity problem. Then we have we persist the data in a MongoDB database with a head of signals, and also have a Grafana dashboard for statistical analysis. Now I will just want to give some conclusions about why we use FiWare and how FiWare helped us on this work. So basically, it solves our problem, our connectivity problem. When we talk about IoT, this is a main issue, the connectivity. So this was solved by FiWare. Also, most traditional businesses need to have affordable systems. They are mainly focused on production, and taking this digital transformation is a big step for them. FiWare could solve both of these problems, and so we could deploy in less than a year with a relatively small team, a simple infrastructure with a fully functional proof of concept that is still operating in the production line. The system is completely distributed along the production line and provides the operators and then the end users a comprehensive way to gather data from the process and understand its business accordingly to the data. So basically, also mentioning that this is a wide open source community that will that is good to understand that is going to.
Great. Thank you, Magno. We are running out of time, but I have some questions. Let's start first with Jose Antonio, and let's see if we manage to complete the round. My question for your presentation, Jose, is since Eprosima is providing these powerful technologies around the DDS ecosystem and also around ROS2, my guess is that you are also exploring OPC UA system handles or some connections with OPC UA in the future, which is kind of regarding the production ready requirements. of the companies you have as customers, which is the system handle that is being more required in companies? Is the DDS system handle? Is the ROS2? Is the WebSockets system handle? Which is the best one or the most required?
Yeah, lots of people ask us about communicating ROS1 with ROS2, because you might know there's this support for ROS1 until 2023, I guess, 2024. And it is very common that companies are still running their applications on ROS1, and they are slowly adopting ROS2, but, well, their full system is developed on ROS1, and they don't want to spend much time yet migrating the whole system to ROS2, because maybe they don't understand it quite well, or they have to make a big change in the architecture, since ROS2 is distributed and ROS1 relies on a broker. So integration service helps them doing that by allowing to communicate specific topics or services between ROS1 and ROS2. Another big successful use case is that of bringing information from ROS2 directly into DDS and vice versa. And I would say also that changing the ROS2 domain ID, which is very important for ROS2, because it allows you to deploy applications that are logically isolated, so that they don't interact between them. But sometimes you want to share certain information between two domain IDs, and then integration service allows you to easily doing that just by typing a few lines in a configuration file.
Okay, great. Thanks, Des. Then it's clear that this is the time now to start going in depth with the fireware system handle and start to implementing this plumbing between all of these protocols. I have also a question to Orpheus, because I am aware that you are expanding this project you have presented today, now putting a bit more the focus on the control part, on the lowest level part of the system, to implement the actual welding operations in more complex shapes. But my question is, which kind of features would your team consider more useful to have in the fireware catalog, or worth it to develop in order to take the most out of your product in a company like Carel or a new customer?
Yeah, so I think we could extract the most value from fireware through the coupled microservices, which live on the cloud and are used for mainly computationally intensive tasks. We have designed our architecture in such a way. However, for everything that doesn't live in the cloud, for example, the hardware control, as you mentioned, I think we could benefit from Fyros a lot, because it's there, it's working, and we can easily broadcast our process information in NGSI format, which makes it standardized and easily integrable to other services in the fireware ecosystem. And specifically, the fact that we could fairly easily connect it to Grafana and display those time series, for example, the robot poses at any given time. That's actually very useful for us, because we can design around that to develop metrics that quantify the performance of the overall system. And also, just a last addition to my answer is that increasing the amount of context data that we produce it's important to have a standardized format in which we are communicating that in, because a system can get very messy very easily when it becomes big. So having something like being forced in a way to use NGSI is good for us, because then we can easily plug it into other data sinks and easily visualize and consume it back again.
Okay, thanks a lot, Ofres. We are running out of time. I had a question to Magno because now I am aware that some synergies are emerging between some of the projects in DH Square, with the STAR project in Ireland, with HW Flexel in Denmark and Lithuania. I would ask to elaborate a bit on how these synergies are being created, but well, we have kind of 30 seconds. If you can just put some pills on what is happening, and then we are closing the session. Yeah.
Okay, I will try to be quick. Basically, as integrators, we are looking for these common standards that could link different and heterogeneous systems. So what we could see that we could work with them was to explore the potential of Fiverr in connecting all of these components, all of this, because they have really nice tools, robotic tools, flexible grippers that could be linked with our quality inspection systems and work together using this common language, as in traditional integrations, basically giving for instance, the automotive industry, each brand, each manufacturer have its own standard, and having this interoperability between different standards, different components, different devices, it's not very straightforward. So we are looking to a solution to comply with this heterogeneity.
Mm-hmm. Okay. Thanks a lot. I invite you to contact me and even to consider joining us in the robotics working group. And let's see how synergies between all of us can be built. Let's discuss about this during this week or the next one. And only saying to you that thank you, every one of you, for your clear explanations on the projects, and thank you to the audience for joining us and listen what we have to offer in Fiverr for Robotics. Thank you all.
Thank you.
Thank you.
Thank you.